This video will introduce weak acids and bases equilibrium constants. They are given special names of Ka for weak acids and Kb for weak bases. We will also talk about calculating pH of these weak acids and weak base solutions. And we will also discuss taking the negative log of Ka and Kb values to produce pKa and pKb values. There are 6 strong acids to memorize and 7 strong bases to memorize. All the rest of the acids and bases that are out there are weak acids and bases. The difference between a strong acid and a weak acid is that a strong acid completely dissociates in water. It is a strong electrolyte. For example, the strong acid HNO3 completely dissociates in water according to this equation. HNO3 aqueous plus H2O liquid reacts to form NO3 negative aqueous plus H3O plus aqueous. As you can see in this equation, there is only a single arrow designating that reactants are completely transformed into products at the end of the reaction. A weak acid will not completely dissociate in water. It is a weak electrolyte. For example, the weak acid HNO2 will exist in equilibrium with water according to this equation. HNO2 aqueous plus H2O liquid in equilibrium with NO2 negative aqueous and H3O plus aqueous. In this equation, there is an equilibrium arrow designating that there are some reactants and some products in the mixture that are continuously changing from one to the other at equilibrium. This is also true with strong bases and weak bases. Strong bases completely dissociate in water and will be represented with a single arrow. Weak bases will not completely dissociate in water and will be represented with equilibrium arrows. Since strong acids completely dissociate in water, their conjugate bases do not have any effect on the acidic or basic properties of the solution. This is because of the single arrow. The conjugate base will not react as an acid or a base in the opposite direction. Weak acids, on the other hand, are connected to their conjugate bases. In fact, the stronger the weak acid, the weaker its conjugate base. Here is a figure that explains this concept. Weak acid and weak base strength is determined by their Ka or Kb value. The Ka and Kb values for selected acids and bases are included in a table in the back of your book. The bigger a Ka value is, the stronger the acid. In fact, strong acids have Ka values greater than 1. The bigger the Kb value, the stronger the base. And strong bases have Kb values greater than 1. A Ka is just the equilibrium constant of a weak acid solution. We denote the acid with the subscripted A. For example, if we have a generic weak acid, HA, it will react with water according to this equation. HA aqueous plus H2O liquid in equilibrium with A negative aqueous plus H3O plus aqueous. The Ka expression for this reaction is the products raised to their coefficients in the balanced equation divided by the reactants raised to their coefficients in the balanced equation. For this equation, the Ka equals the concentration of A negative times the concentration of H3O plus divided by the concentration of HA. Where did the concentration of H2O go in the equilibrium expression? H2O is a liquid, not an aqueous solution. Remember, only aqueous solutions and gases are included in an equilibrium expression. Liquids and solids are not included in equilibrium expressions. Since HA is our generic weak acid, A negative will be our generic weak base. It is the conjugate base of HA. A negative will react with water according to this reaction equation. A negative aqueous plus H2O liquid in equilibrium with HA aqueous plus OH negative aqueous. The Kb expression for this equation equals the concentration of HA times the concentration of OH divided by the concentration of A negative. This is a Kb expression because it is a base. It produces OH negative, and the subscripted B represents base. Weak acids and bases are lower in energy than strong acids and bases. Because equilibria favor the reaction equation side with the lowest energy species, acid-base reactions will go to the side of the weakest acids and bases. As a rule, the equilibrium of a reaction will favor the side with weaker acids and bases. let's add our weak acid reaction equation and its conjugate base reaction equation together. Then we will have HA aqueous plus H2O liquid in equilibrium with A negative aqueous plus H3O plus aqueous, and A negative aqueous plus H2O liquid in equilibrium with HA aqueous plus OH negative aqueous. We can cancel out the HA aqueous because it is on the reactants in the first and the products in the second equation. We can also cancel out the A negative aqueous because it is on the products in the first and the reactants in the second equation. We are left with 2 H2O liquid in equilibrium with H3O plus aqueous plus OH negative aqueous. This reaction is the autoionization of water reaction, which has a special K value, the Kw, and equals 1.0 times 10 to the negative 14. If we multiply our Ka expression by our Kb expression, we have the concentration of A negative times the concentration of H3O plus divided by the concentration of HA times the concentration of HA times the concentration of OH divided by the concentration of A negative. Then our concentrations of both A negative and HA can cancel out because they are both on top and bottom twice. We are left with the concentration of H3O plus times the concentration of OH negative. This is again the Kw expression, and it equals 1.0 times 10 to the negative 14. So therefore, the Ka times the Kb for a conjugate acid-base pair equals the Kw value. This works for any acid's Ka value and its conjugate base's Kb value, or a base's Kb value and its conjugate acid's Ka value. If we take the negative log of Ka times Kb equals Kw and utilize the rules of logs, we find that the pKa plus pKb equals pKw. We know that the negative log of 1.0 times 10 to the negative 14 is 14.00, so therefore pKa plus pKb equals 14.00 for any acid conjugate base or base conjugate acid pair. Ka and Kb values are very small, so therefore some tables will only list pKa or pKb values. To convert these values into Ka and Kb values, take the opposite of the negative log, or use 10 raised to the negative pKa or 10 raised to the negative pKb. We said before that weaker acids have smaller Ka values. Since Ka and pKa values are inversely related, a stronger acid, which has a larger Ka value, also has smaller pKa values. In fact, strong acids have pKa values around 0. See this figure for more information. To calculate the pH of a weak acid or weak base solution, we will need to utilize equilibrium expressions and ice tables. Since the values of Ka are so small, then the concentration of reactants is greater than the concentration of products, and we say that the reaction is a reactants favored. This means that the reaction will tend to go in the reverse direction, and it will create less products. Since our reaction isn't creating many products, we can assume that our values of the change in the concentration is small as well. We can therefore ignore it when we subtract it from our initial concentrations, and just use our beginning concentrations as the concentrations of the reactants. There has to be a point where we will stop ignoring the change in concentration values and instead use the quadratic equation. The point in this class is if the initial concentration of a solution of weak acid divided by its Ka value is more than 500, then we can ignore the change in concentration. If the initial concentration of weak acid solution divided by its Ka value is less than 500, we cannot ignore the change in concentration, and we will have to use the quadratic equation. This will make more sense when we do problems using these concepts, which we will start now. 1. Predict whether equilibrium lies predominantly to the left or to the right for each of the following acid-base reactions using the chart of relative magnitudes of the Ka of each acid conjugate acid and the Kb of each base conjugate base. A. HCl aqueous plus H2O liquid results in Cl negative aqueous plus H3O plus aqueous. B. ClO negative aqueous plus H2O liquid in equilibrium with HClO aqueous plus OH negative aqueous. C. HNO2 aqueous plus HS negative aqueous in equilibrium with NO2 negative aqueous and H2S aqueous. D. NH4 plus aqueous and F negative aqueous in equilibrium with NH3 aqueous and HF aqueous. For this question, remember that equilibrium will lie to the side with weaker acids and bases. To compare the relative magnitudes of the Ka for the acids and Kb for the bases, use the figure. This figure shows you how the acids and bases are related to each other, but it also shows you the strength of the various acids and bases in comparison to each other as well. For letter A, HCl is a strong acid and H2O is a weak base. Cl negative has no acidic or basic properties whatsoever because it is the conjugate base of a strong acid, and H3O plus is a weak acid. Since equilibrium lies to the side with the weaker acids and bases, it will definitely lie to the right or to the product side. This makes sense. Since this is a strong acid reaction, it will completely dissociate. Also, this reaction doesn't have an equilibrium arrow, it has a reaction arrow, which shows that the reaction will go to completion and will go completely to products. For letter B, find ClO negative on the chart, and you will see that it is a weak base. HClO is a weak acid, but the equilibrium will lie on the side that has the weaker acid or base. By comparing the base ClO negative to the conjugate base OH, we find that ClO negative is the weaker base. Similarly, by comparing the acid H2O to the conjugate acid HClO, we find that H2O is the weaker acid. As a result, the equilibrium will lie predominantly on the left side or the reactant side with the ClO negative and H2O. For letter C, find HNO2 on the chart, and you will see that it is a weak acid, and NO2 negative is a weak base. HS negative must be a weak base, and H2S is a weak acid, but the equilibrium will lie on the side that has the weaker acid or base. By comparing the acid HNO2 to the conjugate acid H2S, we find that HNO2 is a stronger acid. By comparing the base HS negative to the conjugate base NO2 negative, we find that HS negative is a stronger base. Since equilibrium lies on the side with the weaker acid and base, the NO2 negative and H2S are the weaker of the acid-base pairs. Equilibrium will lie predominantly on the right side. For letter D, find NH4 plus on the chart, and you will see it is a weak acid, and F negative is a weak base. Therefore, NH3 is a weak base, and HF is a weak acid. Remember, the equilibrium will lie on the side that has the weaker acid or base. By comparing the weak acid NH4 plus and the conjugate acid HF, NH4 plus is the weaker acid. By comparing the weak base F negative to the conjugate base NH3, F negative is a weaker base. As a result, the equilibrium will lie predominantly on the left side, or the reactant side, with the NH4 plus and the F negative. 2. Calculate the pH and percent dissociation of a 0.10 molar solution of CH3COOH, acetic acid, which is a weak monoprotic acid and has a Ka value of 1.8 times 10 to the negative 5. It tells you it is a weak monoprotic acid. What does monoprotic mean? It means that it only has one proton to lose, so it is a weak acid like we have been studying. First, write the equation for the dissociation of CH3COOH. The reaction will be CH3COOH aqueous plus H2O liquid in equilibrium with CH3COO negative aqueous plus H3O plus aqueous. Since this is a weak acid, we will need an ice table to solve this problem. The first thing you may notice about this ice table is that H2O doesn't have its own column. This is because it is a liquid and it has a constant concentration, so it will not affect the equilibrium position and we can ignore it. To fill in the ice table, we know we start with a 0.10 molar solution of CH3COOH, and we can assume that we start with zero concentrations of both products. Since we have zero concentrations of both products, we know we have to form those products in the reaction and use up some reactant. Our changes will then be minus X, and plus X respectively. To find the equilibrium row, add the initial and change rows. Our change for the CH3COOH will be 0.10 minus X, and our change for both products will be X. Now plug these equilibrium values into our Ka expression for this weak acid. Our Ka expression for this weak acid will be the concentration of CH3COO negative times the concentration of H3O plus divided by the concentration of CH3COOH. Remember, we ignore the concentration of H2O in the equilibrium expression because it is a liquid. So we have X times X divided by 0.10 minus X, which equals X squared divided by 0.10 minus X. This equals 1.8 times 10 to the negative 5, which is the Ka value. To solve this equation the traditional way, we will need to utilize the quadratic equation, or we can use our shortcut method of assuming that our change in concentration will be very small, and we can ignore it when we subtract from our initial concentration. First, let's test and see if we are past the point where we can ignore this change in concentration. The point in this class is if the initial concentration of the solution of a weak acid divided by its Ka value is more than 500, then we can ignore the change in concentration. If the initial concentration of the weak acid solution divided by its Ka value is less than 500, we cannot ignore the change in concentration, and we will have to use the quadratic equation. The initial concentration is 0.10 molar, and the Ka value they give you in the problem is 1.8 times 10 to the negative 5. 0.10 divided by 1.8 times 10 to the negative 5 is 5,556. It is more than 500, so we will ignore this change in concentration. Then our equation turns out to be X squared divided by 0.10 equals 1.8 times 10 to the negative 5. Solve for X by cross-multiplying. Then we have 0.10 times 1.8 times 10 to the negative 5 equals X squared. X squared equals 1.8 times 10 to the negative 6. X equals 1.34 times 10 to the negative 3. So, since we have our value of X, we also have our H3O plus concentration, which equals X. Take the negative log of H3O plus, or the negative log of 1.34 times 10 to the negative 3. We have 2.87, which equals our pH. To calculate percent dissociation, which equals the amount that is dissociated during the reaction, this equals our value of X divided by our initial concentration times 100%. So it equals 1.34 times 10 to the negative 3 divided by 0.10 times 100%, which equals 1.34%. 3. Urea, H2NCONH2, is a weak organic base. If the pH of a 5.6 times 10 to the negative 3 molar solution of urea in water is 5.90, what are the values of Kb and pKb for this compound? First, write the equation for urea and water, which is H2NCONH2 aqueous plus H2O liquid in equilibrium with H3NCONH2 plus aqueous plus OH negative aqueous. Since it is a weak base, we will need an ice table to solve this problem. Again, notice that the H2O doesn't have its own column because it is a liquid and can be ignored in equilibrium expressions. The initial concentration of urea is listed. It is 5.6 times 10 to the negative 3 molar. We can assume that the initial concentrations of the products are 0 molar. Since the initial concentrations of the products are 0, we are forming them and using up some of the reactants. Therefore, our change is minus X and plus X respectively. Add the initial and change rows to get the equilibrium row. For urea, it is 5.6 times 10 to the negative 3 minus X, and for both products, it is X. Now write the Kb expression for this base. It is the concentration of H3NCONH2 plus times the concentration of OH negative divided by the concentration of H2NCONH2. It equals, according to our ice table, x times x divided by 5.6 times 10 to the negative 3 minus x, which equals x squared divided by 5.6 times 10 to the negative 3 minus x. This equation equals our Kb value, which is what we are trying to solve. To solve for this, we need to find the value of x, which we can do because they gave us the pH of our solution. It is 5.90. Our x value equals our concentration of OH negative. To find the concentration of OH negative from our pH, utilize the equation pH plus POH equals 14.00. Then our POH equals 14.00 minus our pH, or 14.00 minus 5.90, which equals 8.10. Our OH negative concentration then equals 10 raised to the negative POH, or 10 raised to the negative 8.10. This equals 7.94 times 10 to the negative 9, which equals our x. Plug this into our Kb equation, and we have 7.94 times 10 to the negative 9 squared divided by 5.6 times 10 to the negative 3 minus 7.94 times 10 to the negative 9, which equals our Kb value. Kb equals 6.31 times 10 to the negative 17 divided by 5.60 times 10 to the negative 3. Our Kb value is therefore 1.1 times 10 to the negative 14. To find the pKb value, take the negative log of our Kb value or the negative log of 1.1 times 10 to the negative 14, which equals 13.99.